In a previous video on Gauss's law, we had a bit of an issue that we were discussing, namely on the right-hand side of Gauss's law, the side that involves finding the enclosed charge. A little bit of a rub about exactly what it means to find that enclosed charge, because dimensional analysis would tell you that if you just simply, in say a three-dimensional case here, if you multiply a three-dimensional charge density by a volume, you get the enclosed charge. And indeed, in some cases you will. Then there's this other issue of doing it with an integral like that, where instead of just multiplying rho times v, you multiply rho times dv. So my hint or suggestion to you as you go through this class here is that to sort of maybe trust this version of the enclosed charge a bit more than this one does here, because this one is always right. This one is always sometimes right. I'm trying to highlight the differences between these two to you right now. So it sort of goes like this. We're going to work two problems sort of in parallel right here. I've got these two columns set up here, and what I have is two spheres. Now I'm going to just dispense with the three-dimensional drawing on the two-dimensional paper because it almost never works, and so I'm not even going to try anymore. It just looks too messy in the end. So I'm just going to draw these circles like this. There's a sphere here and a sphere here. There's just a cut or a cross-section of the sphere. This sphere over here has a charge density that's constant, some number A. Now I don't know what A is. It could be 10 coulombs per cubic meter or something like that. I don't know what it is, but just a constant number. So what that means is that no matter where you look inside this sphere here, the charge density is a constant. So just this nice constant thing where if I was going to sort of start drawing charge with this pink pen like this is what it would look like. Nice and uniform and constant throughout. There's no trends or patterns, no matter where you look in the sphere or where you exist in the sphere, any direction, it always looks the same. That's what constant charge density means. Now you come over to this side over here where you have a sphere. Now this one has a linear charge density. So I'm using the constant A again. They can or don't have to be the same between the two columns in here. But the point is that rho now is a function of R. It's not just constant anymore, so it depends linearly on R. If you want to think of this as a line here, A would be the slope of the line, wherever the case may be. But if you look at it very carefully, what does the charge density look like inside this sphere? Well, A is a constant, and it depends on R. So when R is 0, you're right here at the center of the sphere, there is no charge. So at the very center of the sphere, there's no charge. But what happens is you start moving out as R grows, the charge density gets denser and denser. So what this is going to look like is very light, sort of in these smaller R's right here, but as you move out, the charge density get heavier and heavier and heavier until it looks like something like this. It's incredibly hard to draw, but very light near the center, but as it moves out, it gets heavier and heavier and heavier, and in all directions, sort of symmetrically, as the sphere exists, this is sort of what it looks like here. This is what it means to have a non-uniform charge density. So you can draw as many of these lines as you want here. It's kind of hard to do, but you would imagine like if you're using Photoshop or something, you drew a sphere and filled it with some sort of linear gradient that got heavier as you went out. Well, that's what the charge density inside this sphere looks like. So you can see there's very different charge densities. Same spheres, same size spheres, same material sphere, everything, but the charge density is different. This one's constant, looks uniform throughout. This one has a linear dependence about it. So the first thing, of course, we know that we do with Gauss's law is we draw a Gaussian surface in there. Let's just say that the goal of this problem here is to find the electric field inside either one of these spheres. So all right, let's just draw a nice Gaussian surface inside this sphere. There it is. And a Gaussian surface inside this sphere as well. There it is. So although I'm drawing circles, remember these are all actually supposed to be spheres, but I cannot draw 3D on a 2D plane at all. And furthermore, the radius of either one of these Gaussian surfaces here will just sort of be some radius R and some radius R like that. So what I'm doing here is we're finding E at some position R where R is less than capital R, where capital R is the radius of the big black sphere. So these big black spheres here have a big radius of capital R, something like that. So they're identical. So what we're doing, we're finding E at some place R less than R. Okay? So remember that the right-hand side of Gauss's law that we're working on calls for you to find the enclosed charge. What charge is enclosed by these red Gaussian surfaces here. So you can just tell by looking at them they're going to be different. This one has that uniform charge density. So everywhere inside the Gaussian surface, the charge density is pretty uniform. And you can sort of look at it and go, well, there's so much charge enclosed. And at sort of a really low level, you could just count my pink dots there and get an estimate of the charge, whatever. Over here, you can just tell it's going to be different because of this charge density. Because this Gaussian surface sort of surrounds this weird charge. It's very, very light in the center and gets heavier as you go out. You can just look at the two and tell it, well, I don't know what the charge density is going to be necessarily, which one is more or less, but they're just going to be different. You can tell that. So it's the same sphere, the same radius sphere, but this one and this one have different charge densities, and so the enclosed charge is going to be different. So this is why you have to be careful how you proceed. So what we'll do then is we'll just sort of go ahead and use this one over here, and I'll contrast with that one in just a second here. So we can come here and we'll go, okay, fine. The enclosed charge then is a three-dimensional thing, so we will need these three integrals like that. And what it's going to come out to be then is the rho goes in there. I'm just following this prescription right here. And we're in our spherical geometry because this is a sphere right now. So let's go ahead and draw and put in dv in spherical coordinates, which we know is r squared sine phi d phi dr d theta, something like that. That's the dv in spherical coordinates. You can pick it up in your calculus book. Wikipedia has some nice examples of it, whatever. And by the way, this dv would be entirely different if it was a cylinder. You'd have to use a dv in cylindrical coordinates, or if it was rectangular, you'd have to use dv in rectangular coordinates. All these types of problems tend to pop up. The ones for the sphere just seems to be sort of the most fun at the moment, so we're just going with that one. Now what you do, if you look at it very carefully here, the way this all works out here is we know that rho is a constant. It's just a. So rho doesn't depend on r, doesn't depend on how far you are from the center of the circle, doesn't depend on phi, which is the polar angle around the z-axis, and also doesn't depend on theta, which is the azimuthal axis that comes down from the z-axis. It doesn't depend on any of those because it's just a constant. So what that means is you can go ahead and pull your rho out in front of the integral. And you're still left with the 1, the 2, the 3, the r squared, the sine phi, the d phi, the dr, and the d theta. Okay? So you do have an integral to do. Now there's a couple of things you can do. You can just sort of freak out and say, I can't do this, or you can just go ahead and do the integral. The outer one is the d theta, and for the spherical coordinates here, the theta always extends from 0 to pi. That's something you can also sort of look up on Wikipedia limits here. 0 to pi. The next limit is the r, 0 to r, and the last limit here is the phi in here, and that goes from 0 to 2 pi. So if you went ahead and did this, what you would get is 4/3 pi r cubed. Now I didn't do the integral, and I certainly can't do them magically like that in my head, but what I do know is these integrals are just calling for the volume of a sphere, and I know the answer just from good old SAT days, the volume of a sphere is 4/3 pi r cubed, so I have my answer in there. So what that tells me then is that the enclosed charge is rho times 4/3 pi r cubed. That's my answer. That's the enclosed charge for this sphere. But let me just back up just a minute here because I did want to go only to some limit r within the sphere. And so instead of integrating to the big R right here, let me go to the little r. So I just have to make one small change here to my answer right here. Instead of having the r cubed in here, the big R, I want a little r cubed. Because as problem stated here, I want to be able to choose my variable r that I put my Gaussian surface at that isn't necessarily all the way at the boundary of the sphere. So I'll just put a little r in there. Now if you look very carefully at this, you might get a little suspicious about why are we wasting so much time with all the integrals and stuff. Because isn't this just rho times v? Because like I said, this term here is just the volume of the sphere, so isn't that just rho times v? Isn't that the version over here that I cautioned you not to use? And so yes, in fact it is. But the only reason I was able to get away from it in this case here is because rho was equal to a, which is equal to a constant. Only when you have these constant charge densities can you fall back on the simpler definition. But you either have to be very aware of if the charge density is constant or not, or just not use it. Okay? So this was the safe way. It will always give me the right answer no matter what. So in either case, I've completed sort of my left-hand side version of what's required by Gauss's law by getting my enclosed charge. So if you want to just quickly finish up the problem then, I have my left-hand side here. Remember, the right-hand side is going to be sort of, if you watch another video, we're going to claim you can always boil those things down to an integral that looks like this, the surface integral over the sphere there. Now I'll go ahead and fill in the right-hand side. It's rho times 4/3 pi r cubed, and don't forget there's a divided by epsilon naught, as called for by Gauss's law. Now this side right here is the left-hand side of Gauss's law, and we have another video on that which you're certainly welcome to watch, but that's going to be the surface area of that Gaussian surface, not the volume. And the surface area of a sphere radius r is 4 pi r squared. So all that's equal to rho times 4/3 pi r cubed divided by epsilon. I will leave and stop this side here because I believe that you can solve for E now using some algebra, and many things cancel the 4s, and there's going to be an R cancel and that sort of thing. But nevertheless, when this is done here, you will have found R, E, which is a function of R. You will have found the electric field at some point on the interior of this sphere, given that constant charge density. Now let's head over to the other one over here. It has this non-uniform charge density. We're going to start about the same way. We're also going to use this here. We're going to say the enclosed charge is 1, 2, 3 integrals. Now rho is not going to be, there will be a rho in here as stated here, but it's not constant anymore. In fact, rho is a times r. So there's my rho going in, and there's an r squared sine phi, d phi, dr, d theta. So you can see the difference already, how what's the integrand is becoming different. Where before this was a row that I was actually able to pull out in front of the integral over here. Remember, the row came out because it was a constant, just pulled it out. The only thing I can pull out is a, because a is still a constant, but look, I have an extra r in there. So as I go to the very next line here, I'll have the a here, and I've got my 1, 2, 3 dancing worms in there. This is going to become an r cubed times a sine of phi, d phi, dr, and a d theta in there. Look at how different the integral is now. Here I have the triple integral over r squared sine theta, blah, blah. Here's the integral of r cubed over sine phi, blah, blah, blah. So it is a very different integral now, and that's the nature of this beast. That's the nature of this lesson, what I hope that you get here, that when this charge density is not constant, this just will not work for you. Okay? And we'll contrast that a bit more when we're done. Let's just continue on with the integral now. Once again, the limits are all the same and so on as we go. So the theta integral here is going to run from 0 to pi. That's the last one. The r integral is going to run from 0 to little r, the extent of my Gaussian surface. And the inner integral here, which is phi, is going to run from 0 to 2 pi. Now, I just know or remember from previous work that all I have is this r cubed in here. When I integrate all these angular variables, the sine phi and the d theta here, it just generates a 4 pi for me. So what I'm left with here is a 4 pi times the a. Remember, the a is in there, and I'm left still with one last integral from 0 to r of r cubed dr. And I just hope you can remember where that r cubed came from. It came from the r squared, which is part of the differential volume in spherical space, times another r, which is the r that came from the charge density. So the integral is pretty easy to do here. 4 pi a is going to be r to the 4th power over 4. The 4's cancel, so I get this charge enclosed here, which looks like pi a r to the 4th power. Okay, that's my enclosed charge, so I've got it there. Okay, so if you wanted to go ahead and continue on with Gauss' law the way we did over here, we can just sort of continue on here. All of this stuff is going to be the same down to this line right here. Let me see, make sure you can see that here. So I can definitely write e the 4 pi r squared. This is the surface area of the Gaussian surface as needed on the left-hand side of Gauss' law. And now everything can be written as needed over here. In particular, my enclosed charge is now pi a r to the 4th power, and all that is over epsilon. So I will leave it to you. This is the times here. I'll leave it to you to finish up the algebra here. But once again, you will get e, and it will be sort of a function of r also, but a very different function. You can just look at it and see how the functions are going to be different that end up coming out of this here. Okay? So before we wrap this video up here, I just wanted to contrast this line with something here, and then suppose then that you fell back on this definition right here. This is the only thing you could remember, or you forgot to study it, or whatever. Suppose I just said the enclosed charge then was rho times v. I say, okay, this is easy. My enclosed charge is rho, which is a times r. And my v, well, you're thinking, well, it's just v. It's the volume of the Gaussian surface. So you go ahead and write 4/3 pi r cubed in there. And you can see how you're getting a different answer here. This enclosed charge is not the same as this enclosed charge here. It looks like, yeah, nothing's cancels. Pi a r to the 4th power is right. So you're going to get the r to the 4th power, probably luckily in there, but you are not going to get the right constants. The 4/3 and the a and stuff are sort of in different combination in there, so you will get a different answer. So which one is right? This one is right. This one is wrong. Even though you can sort of go through it and work it out, this is just not the right answer. And the reason being is because this definition does not work if rho is not constant. It just doesn't work. So you sort of have to get straight in your mind which one you want to use, because you can see you just missed the whole problem. If you put that enclosed charge down in here and then cancel with the r stuff, you're just going to get the wrong answer. So that's the contrasting sort of story about Gauss' law and how to work on that right-hand side, in particular the enclosed charge. I would strongly recommend always sticking with this one here and just sort of falling back on your calculus and pulling things that appear to be constant out of the integral, leaving things that aren't constant in the integral, as opposed to sort of memorizing this one, which only works in one very specific class of problems. So there you go.